In this problem, we're going to use the first derivative to help us sketch sine squared plus cosine. This function is built up from the trigonometric functions sine and cosine. One of the key features of sine and cosine is that they are periodic. So if I extended the graph of sine from 0 all the way out to, say, 4 pi, then I just have to copy the picture I saw from 0 to 2 pi to see what the graph is going to look like from 2 pi to 4 pi, and so on. Since our function is built from squaring sine and adding cosine, it's also going to have period 2 pi. Which means that once we figure out what the graph looks like between 0 and 2 pi, we can just copy that over between 2 pi and 4 pi, copy that over between 4 pi and 6 pi, and so on. One of the standard calculus steps in figuring out what the graph of a function looks like is to take the derivative, set it equal to 0, so you can determine where the function's increasing and where. We'll use the chain rule to compute the derivative of sine squared, giving us the 2 sine x times the derivative of sine, which is cosine, and the derivative of cosine is just negative sine. When you simplify that, you see that there's a sine of x in both of those terms, which we can factor out, and then we clean it up to get sine of x times the quantity 2 cosine x minus 1. To figure out where the derivative is 0, we just have to set sine of x equal to 0 and 2 cosine x minus 1 equal to 0, which is the same as saying when is cosine equal to a half. Sine equals 0 at x equal to 0, pi, 2 pi, and so on. However, since our function is periodic, we really only need to know the answers between 0 and 2 pi. Same thing, cosine equals a half at pi thirds, 5 pi thirds, and so on, but because it's periodic, we only need to know the values between 0 and 2 pi. If that step feels a little bit confusing to you, I would really recommend you spend a little bit of time reviewing some of the famous angles and famous outputs of the trigonometric functions. So we've taken the derivative and we found that critical points, the places where the derivative equals 0, are 0, pi thirds, pi, 5 pi thirds, and 2 pi. To help us out, I graphed sine and I graphed cosine, and I highlighted where cosine of x equals a half. Between 0 and pi thirds, sine is positive, and cosine is bigger than a half, so our derivative is going to be positive. Between pi thirds and pi, sine is still positive, but cosine is now less than a half, so the derivative is going to be negative. After that, we get a positive and a negative. And one of the things I'd really like to highlight is, because it's periodic, we know exactly what would happen if we extended this chart a little bit to the right or to the left. Just to the right of 2 pi, we are going to see the exact same answer we saw just to the right of 0. And so we know that our function's derivative is going to be positive right there. And similarly, we know just to the left of 0 is the exact same as just to the left of 2 pi, so that's negative. And so all told, we can see we must have a local minimum here, local maximum at pi thirds, a min at pi, a local max at 5 pi thirds, and a local min at 2 pi. In order to graph this function, we need to know the x and y coordinates of all of those critical points that we already previously determined. So, for f of 0, we plug 0 into sine and get 0, 0 into cosine and get 1, so f of 0, and similarly f of 2 pi, is 1. F of pi thirds, you run through the same computation, remembering that sine of pi thirds is root 3 over 2, and you get 5 pi fourths. F of pi is a negative 1. F of 5 pi thirds, same sort of computation, we get 5 pi fourths. I went ahead and plotted those points on this beginning of a graph, and now we just have to connect the dots. We got to get from 1 up to 5 pi fourths, drop down to pi, y coordinate of minus 1, head back up, and back down, and then we can remember that we're periodic, So if we continue this graph, it would continue looking something like that. Having discovered all of these basic features, I can now use a program like Mathematica to help me make a very pretty graph of what this function is going to look like. That's what I've tried to do here, highlighting the critical points and highlighting the fact that it's periodic. That is, it repeats every 2 pi steps.